In previous videos, we saw how Carnot's study of the steam engine inspired Clausius to formulate the first law of thermodynamics. This law states that internal energy, heat, and mechanical work are all different forms of energy, which can be converted into one another. We saw that internal energy and mechanical work can be related to each other with kinetic theory, to which Boltzmann in particular made major contributions. According to kinetic theory, internal energy basically describes the kinetic energy of molecules at the microscopic level, which explains why it can be converted to mechanical work. But then the obvious question remains: how do we explain the relation to heat? Why can heat be related to internal energy and mechanical energy? To answer this question, we must first note that radiant heat is a form of electromagnetic radiation, the same type of radiation as light. To see that indeed light and heat are of a similar nature, we can for example consider the effect of a magnifying glass. A magnifying glass focuses light into one small spot, but it also focuses heat in one spot, because we can use a magnifying glass to start a fire. So we see that light and heat are affected by a magnifying glass in the same way. Another convincing piece of evidence that indicates that heat and light are of a similar nature is by separating the spectrum of sunlight with a prism. We see the different colors of light contained in sunlight spread out from violet to red. As we move a thermometer from the violet side to the red side, we see that the temperature increases. But we see that if we move the thermometer even beyond the visible red light, the temperature still increases. This implies that light and heat are part of the same spectrum, with the difference that light is visible to us, whereas heat is not. This experiment was performed by William Herschel in 1800. What this means in particular is that, just like light consists of rays with a certain wavelength or color, heat also consists of rays with a certain wavelength or color. The first law of thermodynamics thus indicates that light and heat can increase the momentum and kinetic energy of molecules. So by conservation of momentum and energy, electromagnetic radiation must carry momentum and energy as well. And indeed, radiation pressure can be derived from Maxwell's laws of electromagnetism. In the following, we will investigate the properties of radiation in a similar way in which we previously investigated the mechanical motion of a large number of molecules. To see why these topics are similar, consider the velocity distribution of randomly moving molecules. If initially all the molecules have the same velocity, then after some time and random collisions, the molecules will have different velocities. We saw that the velocities of the molecules will follow a particular kind of distribution, called the Maxwell-Boltzmann distribution. This is the distribution that corresponds to the state with the highest entropy. The shape of this distribution depends on the temperature. For low temperatures, the molecules have on average a low velocity, while for higher temperatures, the molecules have on average a higher velocity. By analogy, consider how radiation energy is distributed over different frequencies, or wavelengths, or colors of radiation. Imagine we shine intense light of a single color on an object. The object will then heat up to a certain temperature. Just like molecules randomly exchange momentum and energy in random collisions, radiation in a hot object gets randomly absorbed and emitted. So a hot object emits heat with a certain spectrum in the same way that the velocities of randomly colliding molecules follow a certain probability distribution. Just like in the case of the molecular velocity distribution, this spectrum should be such that the entropy is maximized. And just like in the case of the molecular velocity distribution, the spectrum depends on the temperature of the object. For low temperatures, the emitted radiation has on average a lower frequency or longer wavelength. For high temperatures, the emitted radiation has on average a higher frequency or shorter wavelength. Practically speaking, this means that objects with low temperatures emit heat, which is invisible to our eyes. But as you raise the temperature of the object, it starts glowing. It emits visible light. First, it emits red light, which has a low frequency, and as the object gets hotter, the light gradually turns yellow, and then white, and then blue. This fact is for example used to infer the temperature of a star from the color of the light that it emits. Radiation that follows such a spectrum is called blackbody radiation. It is named so because this type of radiation is emitted by an object that perfectly absorbs radiation of all frequencies and perfectly emits radiation of all frequencies. Such an object absorbs all the visible light, and at low temperatures it emits infrared light, which is invisible to us, so it appears black. Hence, such an object is called a blackbody, and the radiation that it emits is called blackbody radiation. Our ultimate aim will be to find and understand the exact formula for the spectrum of blackbody radiation. This formula was found by Max Planck in 1900 and marked the start of the development of quantum theory. But to get to that final result, we first need to learn more about the thermodynamics of light. First, let's recall what we derived in a previous video about radiation pressure that is exerted by electromagnetic waves. We found that the direction and magnitude of the energy flow of an electromagnetic wave is given by the Poynting factor, which is calculated by taking the cross product of the electric and magnetic field. Dividing this factor by the speed of light c gives the radiation pressure. These expressions give the instantaneous energy flow and pressure of a rapidly oscillating electromagnetic wave. But practically, we do not care about these rapid oscillations, and we only care about the time-averaged intensity and pressure. The time-averaged pressure of an electromagnetic wave onto a fully absorbing surface is given by the intensity divided by the speed of light. But if the surface is fully reflecting, or if it absorbs and re-emits the radiation in the opposite direction, then by conservation of momentum, the pressure is doubled. With our knowledge on radiation pressure, we can now start answering the question, what is the temperature of radiation? First, it was experimentally observed that the radiation energy is proportional to the fourth power of temperature. Later, Boltzmann came with the theoretical explanation for this experimental fact. Hence, this law is called the Stefan-Boltzmann law. The first step in understanding this law is to derive the expression for the pressure of a photon gas using our understanding of radiation pressure. Now, why would this law help us understand the relation between radiation energy and temperature? Note that the ideal gas law of a molecular gas relates the temperature of the gas to other parameters of the system. So a similar formula for a photon gas may also help us relate the temperature of radiation to other parameters of the system. Then, with the photon gas law, we used a fundamental thermodynamic relation to find expressions for the entropy and the temperature of radiation. Note that we used the modern terminology photon gas for easy reference, but the derivation is completely classical. We do not assume any knowledge of photons, which only came with the development of quantum theory. Now let's derive this photon gas law. First, recall how we analyzed the ideal gas law for molecular monatomic gas. The ideal gas law was an experimental fact, even though we didn't know exactly what temperature meant. We found out the meaning of temperature by calculating how randomly moving molecules exert pressure on the walls of the container. By equating the resulting expression to the ideal gas law, we found out that temperature is a measure of the average kinetic energy of the molecules, which is equal to the total internal energy divided by the number of molecules. We can substitute this result into the ideal gas law to find an expression for pressure in terms of energy and volume. To arrive at this result, we identified three factors that determine how much pressure the moving molecules generate. These factors are the momentum of a molecule, the return time of the molecule, and the number of molecules. Similarly, to find out the temperature of radiation, we will investigate how much pressure radiation exerts on the walls of the container. We saw that in case the walls fully reflect or re-emit radiation, the pressure is given by twice the intensity divided by the speed of light. The return time will help us determine the total energy of the radiation in the box. Suppose light travels along the x dimension of the box with speed c. The distance it travels is Lx, and the surface area it covers is Ly times Lz. Intensity is by definition energy per unit area per unit time. So to calculate the total energy due to radiation with a certain intensity, we multiply it with the area it covers and the amount of time that radiation passes through that area before it again sees the same radiation that had already passed through it. The area is given by Ly times Lz, and the return time is given by twice the length of the box divided by the speed of light. Multiplying the dimensions of the box with each other gives the volume of the box. Using the expression for the radiation pressure, we now find how the total radiation energy relates to the volume of the box and the radiation pressure. However, this calculation assumes that all the radiation moves in a single direction. If the total radiation energy is equally divided into radiation moving in all directions in three-dimensional space, one can intuitively guess that if the total energy is fixed, the pressure reduces by a factor 3, because of the three dimensions x, y, and z. This conclusion based on intuition is correct, but we can derive it more rigorously. So let's demonstrate that the pressure exerted by diffuse light is 1/3 the pressure exerted by collimated light. To do this, we must consider what happens when radiation strikes a surface at an angle. If radiation strikes an interface at normal incidence, a beam with area A0 exerts a force F0. The pressure is then given by force divided by area. We saw that this is equal to twice the intensity divided by the speed of light. If the beam strikes the surface at an angle theta, two things change. First, the beam covers a larger area. Secondly, only the normal component of the force acts on the surface. Taking these two effects into account, we see that the radiation pressure that is exerted on the surface is reduced by a factor of cosine theta squared. In the case of diffuse light, light radiates equally in all directions. So to calculate the total radiation pressure on the surface, we sum over all incident angles. To describe all directions of incidence, we define the polar angle theta that defines the angle with the surface normal, and we define the azimuthal angle phi that rotates the direction of incidence for a fixed polar angle. When we integrate over all directions of incidence, we define the differential solid angle d omega. It's a patch on a sphere with a radius of 1, so its sides are given by d theta and sine theta d phi. The differential solid angle is given by the surface area of this patch, which is sine theta d phi. We can verify that the integral over all angles gives 4 pi, which is the area of a sphere with radius 1. We saw that in the case of a single angle of incidence, so collimated light, the energy equals the intensity times the area times the return time, which is equal to twice the intensity times the volume of the box divided by the speed of light. Using the expression for the radiation pressure, we find that the pressure is the total radiation energy divided by the volume. Now we consider the case of diffuse light, where light radiates equally in all directions. To calculate the total energy, we integrate over all propagation directions. However, note that radiation gets reflected back and forth inside the box. So for example, the light that propagates in the positive x direction is the same light that will later propagate in the negative x direction, but it only gives a single contribution to the total energy. So to prevent that we count radiation propagating in two opposite directions double, we include a factor of 1/2. We found that the energy of light propagating in a certain direction is given by twice its intensity times the volume of the box divided by the speed of light. For diffuse light, the intensity is the same in all directions, so integrating over the solid angle simply gives a factor of 4 pi. The factor of 2 cancels with the factor of 1/2, which gives us the final expression for the total radiation energy of diffuse light. To calculate the pressure that diffuse light exerts on a surface, we sum the pressure contribution of all angles. Note that the polar angle only goes to pi/2, because for larger values the light doesn't hit the surface. Integrating over the polar angle gives a factor of 1/3. Integrating over the azimuthal angle gives a factor of 2 pi. If we substitute the expression we found for the total radiation energy for diffuse light, we find the result that we were looking for. The radiation pressure for diffuse light is given by 1/3 times the total radiation energy in the box divided by the volume of the box. Using this result, we will now give the theoretical explanation for why the total radiation energy scales with the fourth power of temperature. To make the link with temperature, we use the two expressions that relate energy and pressure to temperature via entropy. These two expressions are together contained in the fundamental thermodynamic relation. This relation contains 5 system parameters: temperature, entropy, energy, pressure, and volume. Once we pick the value of 2 of these parameters, the values of the other 3 follow automatically. For example, if we fix the temperature and volume of the system, then that automatically determines the entropy, energy, and pressure. For our derivation, we choose the 2 independent variables to be the volume and temperature, and the other 3 parameters are functions of these 2 independent variables. The reason why we choose volume and temperature to be the independent parameters is because we're making an important assumption for the photon gas, which does not hold for molecular gas. We're assuming that the total energy can be factorized into an energy density ρ, which depends on temperature only, and the volume of the system. Using the photon gas law we found previously, we find that the energy density is 3 times the pressure, which only depends on temperature and not on volume. Compare this to the case of a molecular gas, where the total energy is directly proportional to the temperature. Using the ideal gas law, we find that the total energy is proportional to pressure times volume, where the pressure depends on both volume and temperature. We start with the fundamental thermodynamic identity. Because we assume the volume and temperature to be the independent variables, we write the energy differential in terms of a volume differential and a temperature differential. Using the photon gas law, we find that the derivative of energy with respect to volume is 3 times the pressure. Collecting the terms with the volume differential gives 4 times the pressure, which according to the photon gas law is 4/3 times energy divided by volume. We can now calculate the partial derivative of entropy with respect to temperature. We write the energy as the energy density times the volume, where only the energy density depends on the temperature. We can also calculate the partial derivative of entropy with respect to volume, where again we can write the energy as the energy density times the volume. We take the derivative of the top expression with respect to volume, and we take the derivative of the bottom expression with respect to temperature. This gives 2 different expressions for the second derivative of entropy with respect to temperature and volume, so these 2 expressions must be equal to each other. We can rewrite this equation as a separable differential equation, and the solution to this is that the energy density is proportional to the 4th power of temperature. Multiplying the energy density with the volume gives the total energy, which is therefore also proportional to the 4th power of temperature. And this is precisely the experimental observation that we wanted to explain. These results that we found can be used to find the expressions for other thermodynamic quantities for the photon gas. For example, we can calculate the derivative of energy density with respect to temperature. This yields an expression for the derivative of entropy with respect to temperature. Integrating this with respect to temperature yields the expression for the entropy of a photon gas. we may choose to rewrite it in terms of energy instead of volume. Substituting this expression in the definition of the Helmholtz free energy reveals that the Helmholtz free energy of a photon gas is equal to minus 1/3 times the energy. Furthermore, using the photon gas law and the expression for the Helmholtz free energy, we find that the Gibbs free energy of a photon gas is 0. To reiterate, even though we call it a photon gas, these derivations are fully classical and make no assumptions of photons, which weren't introduced until the development of quantum theory. We now know how the total radiation energy is related to temperature. However, we saw that for different temperatures, the radiation intensity follows different functions of radiation frequency, in the same way that the molecular velocities follow different distributions for different temperatures. We want to understand what these functions look like exactly. The first step to understanding this is Wien's displacement law. Wien's displacement law states how the frequency, which has maximum intensity, changes with temperature. The derivation of Wien's displacement law consists of the following steps. We consider a container where one of the walls slowly moves inward with a small velocity v, and we see how this will affect the radiation inside it. One thing it does is that it changes the frequency of the reflected radiation due to the Doppler effect. So if light with a certain frequency hits the wall at a certain angle, then depending on the angle and the velocity of the wall, the reflected light will have a different frequency. Moreover, because the wall is moving, it transfers energy to the reflected radiation. This means that the reflected light will have a higher intensity than the incident light. Taking these two effects into account, we can calculate how much light will be leaving the frequency interval f plus df after reflection from the moving wall. So if diffuse light within a certain frequency interval hits the moving wall from all different angles, the reflected light will have left that frequency interval due to the Doppler shift. Furthermore, we can calculate how much light enters the frequency interval f plus df due to reflection from the moving wall. If light with certain frequencies hit the moving wall at certain angles of incidence, the reflected light will have a frequency inside the interval f plus df. Once we know how much light leaves the interval and how much light enters the interval, we can take the difference to find the net energy change in that frequency interval. This will yield a differential equation that relates the frequency content of the light to the volume of the box, which changes due to the moving wall. If we assume that the compression is quasi-static, then the system always remains in equilibrium as we're moving the wall, which means the temperature of the radiation always remains well defined. What we will end up with is a formula that gives the energy of light with a certain frequency f if the radiation has a certain temperature T. The derivation will follow the lecture notes by Max Planck on the theory of heat radiation. So let's go through the 4 steps of the derivation, starting with the Doppler shift. The Doppler shift occurs due to 2 boundary conditions, namely that the incident and reflected fields must be the same at the wall, or have a fixed phase shift, and both the incident and reflected fields propagate with the same speed of light c. For simplicity, let's first consider a field at normal incidence. The incident field propagates in the x direction. Upon reflection, the propagation direction switches sign, and the wavelength and frequency can change. Both fields propagate at the speed of light c. The surface at which the 2 fields must have the same value is the wall, which moves in the negative x direction with speed v. We can write down the condition for continuity. Then we fill in the value for x at which continuity must hold. We divide both sides of the equation by k. We use the expressions for the speed of light c to rewrite both sides of the equation. By solving for the ratio of angular frequencies, we find by how much the frequency of light changes upon reflection. Because the wall is moving much more slowly than the speed of light, we can Taylor expand the expression around v equals 0. Now let's see how the Doppler shift depends on the angle of incidence. the incident field propagates in the xz plane. The reflected field also propagates in the xz plane, but because of the reflection, the x component of the propagation direction switches sign. We can write down the equation for continuity, and we can specify that continuity should hold at the wall where the light reflects. We can collect the terms that contain the time t and the terms that contain the position z. Because this equation must hold for any arbitrary z and t, both prefactors must be 0. Now let's define the incident angle theta and the angle of reflection theta prime. The x component of the k vector depends on the cosine of the angle, and the z component depends on the sine of the angle. The same holds for the reflected field. We can use these expressions to rewrite the two equations in terms of theta and theta prime. We can rewrite the first equation using the expression for the speed of light c. We then find the shift in frequency due to reflection from a moving wall. However, this expression involves both theta and theta prime, and we don't know yet the relation between them. For that, we use the second equation, which we can rewrite using the fact that the ratio between frequencies is the same as the ratio between wavelengths. We end up with the following two equations that describe the Doppler shift. To simplify it, we assume that the speed of the wall v is much smaller than the speed of light c. In this limit, the angle of incidence is equal to the angle of reflection, and we can Taylor expand the expression for the Doppler shift around v equals 0. We note down this final result for future reference. Now we will examine how the intensity of light is changed due to reflection from a moving wall. We saw that if light hits the wall at an angle theta, the force it exerts is reduced by a factor cosine theta. The force is given by the radiation pressure times the area of the wall. If the wall moves with a velocity v, it performs an amount of work equal to the force of the radiation times the distance that the wall moves. This work is transferred to the reflected light. So the energy of the reflected ray per unit area is given by the energy of the incident ray plus the force of the incident light times the distance that the wall moves. Dividing both sides by dt and collecting terms gives us the final expression that relates the intensity of the reflected light to the intensity of the incident light. We also note down this final result for future reference. Now we will calculate the amount of radiation energy that leaves the frequency interval f plus df due to reflection from a moving wall. Basically, any radiation within the frequency interval that gets reflected by the moving wall will leave that frequency interval due to the Doppler shift. So to calculate the total radiation energy leaving the frequency interval, we simply calculate all the energy that hits the wall with area A within a time dt. Recall that for diffuse light, the intensity of light is the same in all propagation directions, so it can be taken outside the integral. Now we will calculate the radiation energy that enters the frequency interval f plus df due to reflection from the moving wall. Suppose the incident radiation lies in some frequency interval f prime plus df prime. Due to the Doppler shift, it gets shifted to another interval. The initial interval f prime plus df prime should be such that the radiation gets shifted into the interval f plus df. Recall that as the radiation gets reflected by the moving wall, not only the frequency shifts, but also the intensity. So if the incident radiation has intensity if prime inside the frequency interval df prime, the intensity gets shifted upon reflection by some factor. We see that if we multiply this factor with the initial frequency interval df prime, we obtain the final frequency interval df. So the intensity that enters the interval f plus df we call if df, and it is equal to if prime df, where f prime is such that when it gets Doppler shifted, it becomes f. In the limit of small velocities v, this frequency is f times 1 minus 2v cosine theta over c. Assuming the Doppler shift is small, we can Taylor expand the intensity as function of frequency. To calculate the total energy entering the frequency interval f plus df, we integrate the intensities that will end up in that interval over all angles. Recall that for diffuse light, the intensity is the same in all propagation directions, so this can be taken as a constant outside the integral. Now that we have calculated the radiation energy that enters the frequency interval and that leaves the interval, we can calculate the net change in energy due to reflection from a moving wall. We take the two expressions for the outgoing and ingoing energy that we found previously, and then we take the difference. We see that the difference consists only of the term containing the derivative of intensity with respect to frequency. While deriving the Stefan-Boltzmann law, we derived an expression relating the intensity of the radiation to the energy, and we defined the energy density as energy divided by volume. With these two definitions, we can write the energy difference in terms of the energy density. Note that if the wall with an area A moves at velocity v for a time dt, the volume of the box decreases by a times v times dt. We use this result to rewrite the change in time as a change in volume. Furthermore, we can write the difference in energy in terms of a difference in energy density and a difference in volume using the product rule. We equate this to the expression we found previously. We can rewrite this as an equation involving the derivatives of energy density with respect to volume and frequency. By substitution, we can verify that this equation is solved when the energy density for a certain radiation frequency is equal to the third power of frequency times an arbitrary function f of the third power of frequency times the volume of the box. So we have found an expression for the energy density of radiation as a function of frequency. However, our goal is to relate this to the temperature of radiation, and so far there is no reference to temperature. To introduce temperature in this equation, we recall the expression that we found for the entropy of a photon gas. If we assume that the photon gas is compressed adiabatically and quasi-statically, then the temperature is always well defined, and the entropy remains constant during the compression. Therefore, we can write the volume as some constant divided by the third power of temperature. If we plug this into the expression for the radiation energy density as function of frequency, we find that it depends on a function f of frequency divided by temperature to the third power. Or equivalently, we can write it as some other function f prime of frequency divided by temperature. With this expression, we can now derive Wien's displacement law, which tells us at which frequency the energy density is maximal for a given temperature. Let's call the frequency divided by temperature x. To find the frequency for which the energy density is maximal, we take the derivative of the energy density with respect to frequency and set it equal to 0. We can calculate the derivative using the product rule and the chain rule. When we set it equal to 0, we can divide out the frequency squared and find that we have an equation that depends on x only. Let's say that this equation is solved for a certain value of x, called x0. Then, for any given temperature T, the frequency f0, for which the energy density is maximal, is such that f0 divided by T equals the constant value of x0, and this is precisely Wien's displacement law. So now we understand Wien's displacement law, which tells us for which frequency the energy distribution is maximal at a given temperature. But Wien went one step further and wanted to determine the shape of the entire distribution, not just the location of its maximum. To come up with a formula for the energy distribution of blackbody radiation, he used the following line of reasoning. It was known that an accelerating charge generates electromagnetic radiation, so the frequency of the radiation that is emitted is probably somehow related to the velocities of the molecules. So similarly, the molecules' velocities can be written as some function of the emitted frequency. From statistical mechanics, we know that the molecules' velocities follow the Maxwell-Boltzmann distribution. This distribution contains 1 divided by temperature in the exponent. We previously derived that the energy density is a function of frequency divided by temperature. So we can infer that the expression for the energy density contains the exponential of frequency divided by temperature. Based on the formula we derived previously, it should also contain a factor of the third power of frequency. To find the total energy density, we can integrate over all frequencies, and we find that it is proportional to the fourth power of temperature, as it should be according to the Stefan-Boltzmann law. In fact, Wien originally inferred that there should be a factor of frequency to the third power in order to enforce a match with the Stefan-Boltzmann law. We can also choose to write the distribution in terms of wavelength instead of frequency. We know that frequency equals the speed of light divided by wavelength, so the derivative of frequency with respect to wavelength is proportional to 1 divided by the wavelength squared. Therefore, the distribution as we found it is proportional to 1 over the fifth power of wavelength. The radiation law that Wien derived matched well with the experimental data that was available at the time, and it had some sort of physical justification. However, Max Planck didn't like this derivation, because it used the Maxwell-Boltzmann distribution, which is based on statistical mechanics and kinetic theory. At the time, Boltzmann's statistical mechanics and his statistical interpretation of entropy was not yet widely accepted. Clausius introduced entropy to quantify the degree to which a system has spontaneously and irreversibly transformed. For example, as heat spontaneously flows from a hot body to a cold body, the entropy of the complete system increases. Therefore, it was seen as a fundamental law of nature that entropy in a closed system should always increase. However, in Boltzmann's interpretation, increase of entropy is merely a matter of probability. For example, consider a container with two connected compartments A and B. Molecules are moving around randomly, so due to diffusion, after some time the system settles in a state of maximum entropy, where approximately equal amounts of molecules occupy compartment A and compartment B. But now let's introduce a little demon between the compartments. If a randomly moving molecule happens to go from A to B, the demon lets the molecule pass. But if a randomly moving molecule happens to move from B to A, the demon blocks it, so that the molecules stay in compartment B. What will happen now is that due to random movement of the molecules and just a little bit of intervention from the demon, all molecules will end up in compartment B. The gas has undiffused, and its entropy has decreased. Another objection to explaining the irreversible increase of entropy using molecules that obey reversible laws of motion is Loschmidt's paradox. Suppose you have some molecules that move in such a way that the entropy of the system increases in time. Now let's consider the same configuration of molecules, except the directions of the velocities are exactly reversed. Then the entropy of the system decreases in time. So for each configuration where entropy increases, there is a configuration where entropy decreases. So entropy should either increase or decrease with equal probability. Planck's objection was the following. If we know nothing in advance about the state of the system, then we can speak about it in terms of probability. However, if we know the state of the system, then its evolution is determined by the laws of mechanics, not probability. So we cannot say that improbable states evolve to probable states, which in Boltzmann's interpretation means evolving from low entropy states to high entropy states. We can only say that an initial state, however probable or improbable, evolves according to the laws of mechanics. For this reason, Planck was unsatisfied with the physical justification for Wien's law, which was based on molecular kinetics and the Maxwell-Boltzmann distribution. He wanted to derive the same law, but from different physical principles, namely the theory of electromagnetism and the principle of increase of entropy, which he regarded as a fundamental law that cannot be derived using Boltzmann's statistical mechanics. Instead, he proposed the following picture. From the work of Heinrich Hertz, Planck knew that oscillating charges emit electromagnetic radiation. So he imagined the presence of some sort of oscillators that emit and absorb electromagnetic radiation. He wasn't sure what these oscillators are precisely, but they should have some connection with the actual atoms of the radiating matter. When the charges oscillate, they emit radiation, and conversely, incident radiation will stimulate the charges to oscillate. Planck's goal was to find an expression for the entropy of the oscillators and the electromagnetic radiation. If we also know the energy of the oscillators and the radiation, we can determine the temperature of the oscillators and the radiation using the derivative of entropy with respect to energy. This relation is then used to derive Wien's law, although what we're of course actually doing in practice is using the already known Wien's law to find the expression for entropy, and then use that expression as the physical foundation of the theory. When coming up with an expression for the entropy, Planck made the following considerations. We expect the expression for entropy to be similar to the one that was known from the thermodynamics of gases. When the system is in equilibrium, the entropy should be maximal, and it should correspond to the state where radiation is emitted and absorbed at equal rates. So let's find an expression for the entropy of the oscillator, starting from Wien's law. Wien's law states that in equilibrium, the intensity of electromagnetic radiation that is emitted at a certain frequency and temperature is proportional to the third power of frequency times an exponential that depends on frequency divided by temperature. If an oscillator vibrates at a frequency f and has energy UF, then one can verify through dimensional analysis that the emitted intensity is the oscillator energy times the frequency squared divided by the speed of light squared. Since we know the intensity from Wien's law, we can infer that the oscillator's energy is proportional to frequency times an exponential that depends on frequency divided by temperature. To infer the oscillator's entropy from this, we use the fact that 1 divided by the temperature equals the derivative of entropy with respect to energy. We use the expression for the oscillator's energy to find the expression for 1 divided by the temperature in terms of the oscillator's energy. If we integrate this expression with respect to energy, we find the entropy of the oscillator. In an attempt to justify this formula for the entropy of an oscillator on more fundamental grounds, Planck analyzed the entropy change of an oscillator absorbing energy from a stationary radiation field. He came to the conclusion that the fundamental starting point for deriving Wien's law should be the assumption that the second derivative of the entropy of the oscillator with respect to its energy should be proportional to 1 divided by the frequency times the energy. So Planck tried to derive Wien's radiation law from electromagnetism and the principle of increasing entropy, whereas Wien's starting point was the Maxwell-Boltzmann distribution from molecular kinetics. But then, new experimental data came in that contradicted Wien's radiation law. It turned out that for small values of frequency over temperature, Wien's radiation law failed to match the experimental observations. So Wien's law fails at high temperatures or long wavelengths, such as deep infrared radiation. How did Wien and Planck respond to this news? Since Wien's starting point was molecular kinetics, he simply argued that at high temperatures, the molecules must somehow move differently. Planck, on the other hand, found this contradiction much more problematic for his approach, and he felt much more urged to address the issue. In retrospect, Planck commented that because he focused on the question of entropy, he could make progress that other physicists couldn't. So let's see how Planck solved the mismatch between his theory and experiments. Recall that Planck's starting point to derive Wien's law was that the second derivative of an oscillator's entropy with respect to its energy should be proportional to 1 divided by the frequency times energy. The resulting Wien's law is valid for large values of frequency divided by temperature. However, for small values of frequency divided by temperature, experimental observations indicate that the radiation intensity is directly proportional to the temperature. The radiation intensity is directly proportional to the oscillator energy, so the oscillator energy is given by some constant times the temperature. Using the relation that 1 divided by temperature equals the derivative of entropy with respect to energy, we find that the entropy of the oscillator should be proportional to the logarithm of its energy. The second derivative of the entropy with respect to energy is therefore proportional to 1 divided by the energy squared. So now we have two expressions for the second derivative of entropy with respect to energy, which should be valid for different limits of frequency divided by temperature. Combining the two expressions, we find a new result that reduces to the original two expressions in the two limits for frequency divided by temperature. So what will be the new radiation law that follows from this expression for the second derivative of the entropy of an oscillator? If we integrate the result with respect to energy once, we should get an expression for 1 divided by the temperature. So let's integrate with respect to energy. Now we can solve for the energy. This result describes how the energy of the oscillator depends on frequency and temperature. To calculate the radiation intensity that such an oscillator generates, we multiply the energy with the frequency squared divided by the speed of light squared. This yields a new radiation law, which turned out to match with the experimental data perfectly. But what is the physical interpretation of this new law? So far, we just changed the second derivative of entropy to make it fit the data, but there was no physical justification for doing this. To physically interpret this new result, let's calculate the entropy of an oscillator according to the new formula we found. To find the entropy of the oscillator, we solve for 1 divided by temperature using the expression for the energy. This, by definition, is equal to the derivative of the oscillator's entropy with respect to its energy. So we integrate with respect to energy to find the entropy of the oscillator. To give this expression for entropy a physical interpretation, Planck turned to Boltzmann's statistical mechanics. Recall that initially, Planck opposed Boltzmann's methods, because he believed they couldn't properly explain the increase in entropy as the second law of thermodynamics required. However, because Planck saw no other way to give a physical explanation for his radiation law that matched the experimental data so well, he nonetheless accepted Boltzmann's approach. So consider the following situation. We distribute n distinguishable packets of energy over n distinguishable oscillators. We saw in a previous video how we can compute the number of ways in which this can be done, and that we can apply Stirling's approximation to simplify this expression. For large numbers of energy packets and oscillators, the multiplicity of the most likely macrostate is practically equal to the total number of ways the energy packets can be distributed. We can calculate the entropy of the total system of n oscillators by using Boltzmann's definition of entropy. We can plug in the expression that we found using Stirling's approximation. We can rewrite it so that it more closely resembles the expression that we're trying to explain. The average energy per oscillator is given by the total energy divided by the number of molecules. Therefore, we can write the number of energy packets m divided by the number of oscillators n in terms of the average oscillator energy. We can plug this into our expression for the total entropy of n oscillators to find an expression for the average entropy of a single oscillator. By comparing this to the expression for entropy that we found from Planck's radiation law, we can now interpret the meaning of the constants A and B. A times the frequency gives the energy of a single energy packet, and B equals A divided by Boltzmann's constant. If we substitute this into the expression for the oscillator energy, we find the term e to the power energy divided by Boltzmann's constant times temperature. This should remind us of Boltzmann factors, which we saw in a previous video. Indeed, a modern derivation of Planck's law typically uses Boltzmann factors. In this derivation, we start with the assumption that the energy levels are equally spaced with some finite interval epsilon. If the oscillator is in thermal equilibrium with an environment of temperature T, then the probability to be in a certain energy state is proportional to the Boltzmann factor, where we can plug in the expression for the energy levels. We can calculate the normalization constant, or partition function, by summing all Boltzmann factors. After plugging in the expression for the energy levels, we can use the formula for calculating a geometric sum to find an expression for the partition function. We know from a previous video that the average energy of a system is found by taking the derivative of the logarithm of the partition function with respect to the thermodynamic beta. Performing this calculation and simplifying this expression yields Planck's formula for the average energy of an oscillator. And if we know the energy of an oscillator, then we saw that we can calculate the radiated intensity by multiplying with the frequency squared divided by the speed of light squared. And we saw that we can calculate the energy density by multiplying the radiated intensity with 4 pi divided by the speed of light. Plugging in the expression for the radiated intensity and the energy of an oscillator, we find a final expression for the energy density of radiation of a certain frequency. However, throughout all the derivations that we performed, we ignored the 2 degrees of freedom due to the polarization of light. So the final result is multiplied by a factor of 2. Now that we got an impression of how Planck came up with this radiation law, let's make some remarks about the historical sequence of events. Some sources on this topic may mention the Rayleigh-Jeans radiation law and the ultraviolet catastrophe as the motivation for finding Planck's radiation law. The storyline goes as follows. We saw in a previous video that for a molecular gas, the equipartition theorem states that the total internal energy is equally distributed over all degrees of freedom. Then, according to classical theory, we can apply the same equipartition theorem to radiation. That is, all the radiation energy is equally distributed over all modes of radiation. Here, every frequency and propagation direction of radiation corresponds to a different mode. If we assume the density of modes is constant in frequency space, then the number of modes around a certain frequency f is proportional to f squared, because all the different possible propagation directions cover the area of a sphere with radius f. So the higher the radiation frequency, the more modes there are, without any upper limit. According to the equipartition theorem, all modes contain the same amount of energy. These 2 observations together lead to the conclusion that the energy must diverge for higher frequencies at any given temperature, which is obviously unphysical. It would imply that a blackbody at a certain temperature would radiate an infinite amount of energy and at arbitrarily high frequencies. Since ultraviolet light has a higher frequency than visible light, this unphysical divergence is called the ultraviolet catastrophe. As the story goes, the quantization hypothesis was introduced to solve this ultraviolet catastrophe. The reason why quantization would solve the ultraviolet catastrophe is this. According to the logic behind the Rayleigh-Jeans law, there are more modes with higher frequency, and if all modes should contain the same amount of energy, then more energy is put in radiation with higher frequency. If we introduce the concept of quantization, then still higher frequencies have more modes. But these modes are more difficult to excite, because the energy should exceed a threshold that becomes higher for higher frequencies. For very high frequencies, that threshold is higher than the total energy of the system, so these cannot be excited at all. This trade-off between the number of modes and how easily each mode can be excited leads to the typical curve that goes to 0 for very low frequencies and very high frequencies, and has a maximum in between. However, this storyline involving the ultraviolet catastrophe is different from the storyline we discussed previously, which involved Wien's radiation law and Planck's argumentation from entropy. This discrepancy between the actual historical sequence of events and the popularized quasi-history of the ultraviolet catastrophe has been the subject of several commentaries. At this point, one might wonder, how important is this historical accuracy anyways? Surely what's truly important is that we properly understand the correct physics, right? However, if at some point you want to take part in making scientific progress, it may be helpful to know what making progress realistically looks like. The problem with quasi-history is that it presents an unrealistic picture of the discovery of new scientific concepts. Either the development appears so obvious that it is trivial, or the discoverer had an inexplicable stroke of genius. In the case of Planck's radiation law, the quasi-history makes it seem as if Planck solved the ultraviolet catastrophe with a single brilliant insight. but that ignores the careful and lengthy examination of different views that was necessary to reach the solution. It downplays the degree to which Planck relied on the work of others, and the fact that Planck had to change his opinion on the statistical ideas of Boltzmann. So let's summarize the differences between the quasi-history and the real history behind the development of Planck's radiation law. The first point on which the two histories differ is what the best radiation law was before Planck's law. According to the quasi-history, it was the Rayleigh-Jeans law, which suffered from the divergence for high frequencies. However, we saw that actually it was Wien's radiation law. It is interesting to note that the Rayleigh-Jeans law wasn't introduced until years after Planck's law. One might wonder why a wrong law would be proposed after the correct law was already proposed years ago. But such is the reality of scientific progress. It doesn't necessarily follow a linear logical structure, but rather it can take quite some time before a correct idea is properly understood and accepted, in the same way that it took time before Planck accepted Boltzmann's statistical ideas. The second point where quasi-history and real history differ is for which wavelength regime there was a mismatch between experiment and theory. According to quasi-history, the mismatch was in the ultraviolet regime, where the theory predicted a divergence in energy, whereas in practice no such thing is observed. However, what actually happened was that the prediction of Wien's law failed in the infrared regime. The third point where the quasi-history differs from the actual history is the way in which the mismatch was solved. According to quasi-history, Planck simply assumed that the energy levels of an oscillator are quantized, and with that assumption, the correct radiation law follows straightforwardly. However, what actually happened is that Planck assumed that the second derivative of the oscillator's entropy with respect to its energy should have a certain form. From that he calculated the radiation law and the expression for the entropy of an oscillator. He then reluctantly turned to Boltzmann's statistical mechanics to give this expression a physical interpretation. Now let's summarize what we've seen in the past few videos. We started with the steam engine. Its invention had a major impact on society during the Industrial Revolution, which motivated scientific research on this topic. Sadi Carnot made the following two observations. First, the steam engine can be abstractly represented as a heat engine. Heat flow is used to perform mechanical work. Second, the most efficient heat engine is one that is reversible. Clausius took these observations and elaborated on them further. Firstly, he identified that internal energy, heat, and mechanical work are different forms of energy, which can be transformed into one another, while the total amount of energy remains conserved. This is the first law of thermodynamics. Secondly, he quantified the degree to which a system has irreversibly transformed by introducing the concept of entropy. The second law of thermodynamics states that in a closed system, entropy can never decrease. Then came the development of kinetic theory and statistical mechanics, where Boltzmann in particular made major contributions. By interpreting internal energy as the kinetic energy of molecules, it is explained why internal energy can be converted to mechanical energy. Entropy can be interpreted as the probability of a certain configuration of randomly moving molecules. Spontaneous increase in entropy is explained by the idea that randomly moving molecules spontaneously evolve to statistically more likely states. Having explained the relation between internal energy and mechanical energy, we still need to explain the relation with heat. The relation between kinetic energy and radiation is explained with radiation pressure. To explain why a black body at a certain temperature spontaneously emits radiation with a particular frequency distribution, Planck tried to invoke the principle of increasing entropy and apply it to the electromagnetic theory of radiation. To give a physical interpretation to the radiation law that he found eventually, Planck used Boltzmann's statistical interpretation of entropy. This interpretation involves the assumption that radiation energy comes in discrete chunks of energy. This is why Planck's radiation law will play a fundamental role in the development of quantum theory.